Hello, this is the second of these short presentations and lectures around Introduction to Flow Frequency. In this presentation, we're going to look at flood frequency analysis in particular, focusing on the higher flows that we are most interested in estimating in this project. We'll look again at flow duration curves and think a little bit about flood magnitudes in particular. We'll have a look at ways of looking at only the flood events using annual maxima and peak over threshold approaches, a little bit on the definition of the 1 in 100-year flood, something about stationarity and change through time in series, and a little bit at the end we'll just discuss clustering of flood events. In the two examples on the right here, we have in the top one a very small river, only going up to 7 cubic meters per second, showing very short-lived flood events in response to rainfall, storms, maybe typhoon events, and in some years no significant events at all, whereas in others we get little groups of events. And then in a much bigger river here, where the flows go up to 1,000 cubic meters a second, in some years without high flow events, some years with them clustering together. And generally a little bit of a tendency maybe for there to be more events in the latter half of the data series than the first half. And we'll look at some of those trends in the data as we go through. So a reminder, something we looked at in the first lecture was around flow duration curves. I showed this example from the UK, from Glenorchy, where we have a flow duration curve in black for the whole year, blue for the winter, the wet period, and red for the summer dry period. The scale on the x-axis here is very non-linear, but if we look here at 1% of the time, 3 days a year, we see that the black line, if we go up, would come out at about 200 cubic meters per second. 1% of the time is maybe not the highest, most dangerous floods. If we go to 0.5% of the time, we could then estimate a flood flow for 0.5% of closer to 300 cubic meters a second. So it's this left-hand edge of the flow duration curve that we're most interested in. And as it says here, floods are rare, so they occupy only a very small proportion of the data, well under 5%. We need long data series if we're going to estimate flood magnitude accurately, because there aren't very many big floods, and so we need a lot of data to detect some of them. And of course, analysing all of the data as you do in a flow duration curve means that you get very large data files, which can be difficult practically to analyse. So usually flood magnitude is estimated from a subset of the total data. And the two most commonly used ways of subsetting the data are to use annual maxima, 1 data point per year, and to use something called peak over threshold or partial duration analysis, where you only look at flows that are above some given threshold magnitude. The data that was in this table, on the graph at the top, we have annual maximum discharge on the x-axis here and return period calculated from this equation on the y-axis. And we only have 9 years of data, so it's quite difficult to estimate the return period of the highest events. We can only, using this method, only really go up to a return period of 9 years because we only have 9 years of data. There are ways of improving on that we'll come to later. And we can see that we have a relationship that looks as if it's almost a straight line, except when you get to the two highest flows, it looks as if this relationship steepens up. It either curves or it has two components to it. That might indicate something about this data series. It may actually indicate that these events maybe weren't as big as they potentially could have been, but we don't know that until we do more analysis. At the bottom, we see a similar shape relationship. This comes from data on the River Rhine in Germany and is data from 35 years, so it's a longer data series, again you see a straight line tending to become a little bit steeper at the top. And then these grey and black lines of different types are fitting different statistical distributions to these data to try to make better predictions of the high magnitude event. So we'll look at how we use these sorts of distributions in subsequent slides. 2 points to remember. The recurrence interval or return period is the average number of years. Floods sometimes occur more frequently or sometimes less frequently, depending on when we collect our data. Over a long time period, how long is long, we'll come back to. The average should be is what we're looking for. And the data again assume one flood per year. We're looking for the biggest flood in a given year. It's important that we remember that. A second way of reducing the size of our data sets is to use what's called a peak over threshold or a partial duration series. So what we do is we reduce the size of the data set by only looking at flows that are above a threshold discharge. This allows several events to be recorded for each year. Equally, some years might have no events. What we've got on the right-hand side, just to show how this works, at the top is the original data. Applying a threshold, in this case of 107 cubic meters per second, keeps 5% of the data points. And this is what 5% of the data points look like. There are no data on here below 107, so all these low flows are now missed off. It's only when the flow gets to 107 does it appear on this lower graph. So we lose a lot of low flow periods, but we still retain 5% of the data. If we increase the threshold to only retain 1% of the data, 3.6 days each year, that needs a threshold in this case of 378 cubic meters per second. And you see that we get now a very different picture. We get no events at all in 2006, 2007, a few events in 2008, 2009, a bit of a cluster in 2011, some big events in 12, 13, and then events becoming a bit sparser. This maybe tells us quite a lot about the sequencing of floods in this river. It implies a certain degree of clustering of floods in this period and a drier period here. We can look at the data in a different way. On the left-hand side, we have proportion of data retained as we increase the threshold discharge. The purple here is the bottom plot. You see how we're only retaining 1% of the data. So there's a lot of data, 99% of the data not being used. The red 5%, we're taking this higher part or higher flow part of the data set, and we're ignoring all of this. If we have no threshold, we've got all of these data in here, which are not telling us anything really about flooding and flood risk. So thresholding the data certainly reduces the size of our data set, and we can use this curve to assess what is an appropriate threshold for a different river. 1% is very commonly used for this sort of analysis, but depending on the flow regime, different thresholds may be appropriate. The annual maximum approach has been quite widely used, and just as an example, here are some data from the UK from 10 different rivers in different parts of the country, just showing the annual maximum flood in those different rivers and allowing us to look for correlations, allowing us to say, well, are there particularly wet years? Are there wet periods? Are there dry periods? And I think one of the things you might immediately see from that, those graphs, is that actually there's quite a lot of difference across the country, and we can look at similar data for the Philippines in due course to see how much difference there is as we go from one province to another. So what trends are there in the data? Well, some rivers do have clusters of years with larger floods and clusters with smaller ones. We can see in this example here, we've got periods where there don't seem to be such big floods, but then we get a little group of couple of years there with higher floods. We get a group here of 3 years with higher floods, a group here of 5 years, separated by periods without such high floods. So there's some degree of grouping in the flood events, but there is a lot of inconsistency between the sites. So we can't really detect many trends in these data without doing further statistical analysis. So we might ask ourselves some questions. Why do the rivers not show the same patterns? The UK isn't a very big country. Maybe we should expect similarity. Well, remember that flood events are caused by extreme conditions. Rainfall events, wet periods over months leading up to an event, leading to saturation. And quite small differences in these conditions can have quite big effects on flood magnitudes. They can make the difference between a flood being, in this case, for example, 200 or 300 cubic meters per second. And those sorts of differences are the result of apparently quite small differences in the conditions, either of the rainfall event or of the catchment before the rain falls. Our catchments, of course, have a range of properties, and it's just the same in the Philippines. Locations are different, and so weather conditions are different. In the UK, as we go south to north, it gets colder. As we go southeast to northwest, you have more high terrain, and therefore you tend to get more rainfall induced by those hills and mountains. Weather conditions vary as you move across the country. The same is very true in the Philippines. Geological differences, so soils are different, slope angles are different, rain will run off the landscape in quite different ways in different parts of the country. And catchment size. You can see here we've combined very small catchments where the flow only goes up to about 6 cubic meters a second with some quite big catchments where the flow goes up to 1800. Smaller catchments tend to flood in response to intense rainfall. In the UK, that's often in the summer period, whereas in large catchments, it may mean rain falling for many weeks in a row. It can also involve snow in the UK and the melting of that snow in some of our big northern catchments. So location, geology and landscape, catchment size can all affect the response of rivers to flood generating events, to storms, and in the Philippines case, typhoons. So we should expect some differences. You will often have heard people talking about the 1 in 100 year flood. The 1 in 100 year flood is often used in design. It's used in design of bridges, of flood embankments, of drainage systems, for example, and is a very commonly used reference flood magnitude that is applied when designing those sorts of features. Other frequencies can also be used in design, but 1 in 100 years is very, very common. Our river channels are actually adjusted. In other words, the size of the channels is related to a much smaller event. The bank full flood that just stays within the river in many parts of the world occurs about once every 2 years. It might be once every 1.5 or 5 or 7, but it's quite a commonly occurring event, much smaller than the 1 in 100 year flood. We have to accept, of course, that climate is changing, and the 1 in 100 year flood today might actually become a more frequent event in the future, and planning and design has to be aware of that. And also planners do have to consider what's the worst that could possibly happen. And in flood hydrology, this is the PMF, or the probable maximum flood. The worst conditions you can imagine. In the Philippines case, that might be a series of typhoons with very heavy rainfall, the ground is saturated, and then you get another long-lasting rainfall event on top of already saturated ground. What's the worst that could happen? We don't design structures necessarily to cope with that, but society needs to be able to manage when those scale of events do happen, very rare as they may be. Now, the 1 in 100 year flood isn't always an easy thing to explain to people. Here is a quote from a mayor in the United States who said after the 1965 flood, they told us this wouldn't happen again for another 100 years. Nobody will have said that. What they will have said is that the 1965 flood was a 1 in 100 year event. And that mayor has interpreted that as meaning that it'll be another 100 years before another one occurs. That isn't the case. The 100-year event could have occurred again in 1966 or in 1967. One occurred in 1993. Equally, if you have a very long data period and you wait a few hundred years, there will be gaps of well over 100 years without any floods of that magnitude. So it isn't necessarily the easiest of concepts to explain. And a British engineer, Rodney White, who's done a lot of work in this area, has said this, that the concept of a return period gives no measure of the likelihood of flooding in any given year and can engender a false sense of security. People will think, as this mayor did, oh, we've had a 100-year flood, there won't be another one for another 100 years, I don't need to worry about that. Whereas in fact, the 100-year flood could occur again the following year. As a result, Rodney White and others have suggested that we might think about flood frequency in a slightly different way. We have to remember the 1 in 100-year flood is for a long data series, and it's for one that is stationary. In other words, the mean is not changing due to climate change, for example, and actually the variability is not changing either. You could write the definition differently. It is also the flood which has, on average, a probability of occurrence of 0.01 in any given year. So this year it has a 0.01 probability, next year it has a 0.01 probability, the year after. And so if an event does occur that is a 1 in 100 year event this year, that doesn't change the chance of it happening again next year. It doesn't mean we're going to have to wait another 100 years. It's got the same probability as occurring next year and the year after and the year after as this year. So this might be a way to improve how we explain flood frequency. 1 in 100 years might suggest to people like this mayor that events only occur every 100 years. Whereas a probability-based definition makes it clear that events can occur in any year, including in successive years. On the previous slide, I mentioned stationarity. So stationarity is the assumption, a statistical assumption, that the properties of the data statistically do not change over time. In particular, the mean isn't changing and the variance isn't changing. So if you look at these data, which are on logarithmic scale this time, the mean, does the mean change? Does the variability change? When we look at that data in a different way and plot the variance, we see that the variance seems quite constant. It goes up and down. Maybe towards the end of the data series in the 2000s, there's slightly higher variance. We had quite a prolonged dry period here following on from some quite high flooding. So maybe there is a little bit of a change here in the variability, which is important. But we need to look at both the mean and the variability if we are to assess how stationary a time series is. Because variability is really important in terms of flooding and flood prediction. Climate change is giving us problems, of course, because climate change means that the mean and or the variance may be changing. And if that is happening, it makes it difficult to apply some standard statistical techniques to these sorts of analyses. Even if we do have a stationary data set, though, to estimate a 1 in 100-year flood, how long does our data set need to be? Well, some analysis we'll look at in a later lecture suggests that between 50 and 70 years seems to be long enough. But actually, worldwide, not all that many records are that long. They're getting longer, of course, because a lot of data monitoring started in the 1950s and 60s, so longer records are slowly becoming available as time goes on, but we often have to work with shorter data series, as is the case in the Philippines. We also have to think about how to account for non-stationarity. There are some statistical methods we can use to help us manage non-stationary data sets. We may transform the data, we might filter the data to remove trends, or we may use statistical methods that do not assume stationarity, all of which can help us to understand the data better. Even in a stationary series, though, we do find evidence of clustering. Floods tend to cluster, droughts tend to cluster, and it's been observed for many years that floods actually, even in quite long data series, are not random events. They do tend to be in groups. They tend to group it over short time periods because floods depend on wet conditions. And wet conditions do persist for months or years. Once the soil, once the groundwater is fully saturated, once all of the water stores in a catchment are saturated, it may take months or years for those to start to dry out. And so any rain that occurs during that time will lead to potential flooding. Atmospheric conditions also tend to be persistent. We know about the El Nino Southern Oscillation, for example. El Nino Southern Oscillation, that leads to persistent patterns in the weather, which mean that you get sequences of flood-generating events. And then you get periods with sequences of events that do not generate significant rainfall and flooding. If we look over much longer time periods, we find climate variability, which may be cyclical. ENSO is cyclical over different timescales. We also find evidence in a lot of different parts of the world, several countries, for flood-rich and flood-poor periods. Flood-rich, where floods tend to cluster, flood-poor, where there is an absence of floods. And you can show that statistically clustering is more likely in longer time series than we might expect. And this was described by somebody called Hurst over 100 years ago now, initially looking at data from the River Nile that we mentioned in the first lecture. And the Hurst effect describes this tendency for clustering in time series. So clustering is real, and floods do tend to cluster, which actually is very important for planning. It's also very important how we communicate the risk of flooding to people. If you've had one flood, you're more likely to then get other floods. If you're in a dry period, maybe that dry period will go on for a few years before you get floods. Doesn't mean the risk of flooding has gone away. It's just a group of years together that have less floods than you might expect. A couple of examples on the right just to illustrate how this clustering works. This is the number of typhoons that reach landfall in China, Philippines, Taiwan, and Vietnam added together in different months of the year, and you'll be well aware that it's during the wet season in Philippines that most of the typhoon landfalls occur. But you can see El Nino years, which are the red, are significantly above La Nina years in the early part of the wet season, June, July, August. Whereas when you go into September, October, November, it's La Nina years where you see more landfalls and actually significantly more late in the wet season in October, November. So we can see that there are differences between El Nino and La Nina in the timing, in that case, of typhoon landfalls. And that feeds through into how many floods we get. And in the bottom example, we are dealing with Southeast Asia as a whole, mainland Southeast Asia, so not including Philippines. And here we have floods from all causes in blue from 1985 through to 2015, with quite a big peak in the 2000s through to 2010. Tropical cyclone generated floods, though, actually there weren't so many of those. In fact, there were none in this region in around about 2003. These were floods caused by other purposes, whereas when there are fewer floods overall, tropical cyclones are more important causes of that flooding. And again, we see seasonal patterns in tropical cyclone generated floods. So we see several reasons why we get clustering to do with climate and controls over climate, such as El Nino and La Nina, which are also important here. Those driving cyclones, those driving, to some extent, flood response. So let's have a look at a practical example. This uses a flow duration curve, as you've seen before. It's plotted, the percentages scale goes the other way around. This is percentage of time the flow is less than indicated, which is why the curve goes up rather than down. But it's the same principle as the plots you've seen previously. From a site in the United States, monitored by the United States Geological Survey. And we've got three ways of plotting these data, which are mean annual flood data. We've got all data 1931 to 70 in black. We've got in orange, all data is 1931 to 2006. Orange is 1931 to 1970, the first part of the data series. And then in blue is 1971 to 2006. And if we estimate, for example, the median mean annual flood, the 50% on this axis, we read up here and we can read off the median values of these mean annual floods. All data, we get 60 cubic meters per second. 1971 to 2006, which is the recent time period, in blue is 75. The earlier time period, 1931 to 70, is 49. So if we're going to design a flood embankment for this site in 2020, which of these estimates should we use? Should we use all the data at 60? Maybe we should only use the more recent data at 75. The more recent data is more recent, so maybe it reflects current conditions if climate's changing. It's also higher, so maybe it's worst case, and maybe it's safer to use the worst case rather than the longer term average, which maybe isn't quite so severe, but maybe may lead us to underestimate the flood risk. The issue, though, is maybe the climate is changing and maybe these curves are shifting upwards. If so, maybe to design a flood embankment for the next 100 years, maybe we actually need to go above this. Maybe things are going to get even worse in future. So it's quite difficult to know when you've got non-stationary data that seem to have a trend and seem to have a change in pattern in the round about 1970. Is this the new steady, stable condition and we can use this for design? Or should we assume that things are going to keep getting worse, and should we actually add in another line up here to represent the potential for further climate change? There isn't a simple answer. You have to look at the data for a given site and look at it in the context of what you know about changes maybe elsewhere in the region, elsewhere in the country. A couple of other things that we have to look at, though. There aren't very many data points in the red circle, which is where we're looking at the very rare events. We looked at the 50th percentile here. If we're interested in the 99th percentile, or 1% of worst floods, there really are very few data points, and none of the three data points that are the three highest data points lie very close to the trend lines. They all lie above their trend lines, suggesting that maybe things are a bit worse than we expect at this end of the plot, but we don't know for sure because the data sets really aren't quite big enough long enough rather, to allow us to make definitive conclusions. So the greatest uncertainty is actually in the part of the data set that most affects flood estimation, which makes life a little bit more challenging than we'd like it to be. We'll pick up on some of these themes next time. But for now, thank you.